All right, everybody here, thanks for joining CFRG Research Group meeting for IETF 120 Vancouver. Are your chairs, two of which are here, Alexei Melnikov, Nick Sullivan, who's me, and Stanislav Shishmaev. He is online on the Meet Echo. Mute. Next slide, please. All right, so just some administrative reminders here. The session's being recorded. We do have a minute taker in HedgeDoc. Follow along. Additional contributions are welcomed. Here's the participant guide. These things should all be clear to you for being here at the meeting at the IETF for the last 3 days. The minutes are available right here. And next slide, please. All right, this is the note well. This is the IRTF note well, but it does follow the IETF intellectual property rights disclosure rules. These things should be well known. Read these. If you haven't read these, read them, and we'll move on from there. There's also a code of conduct. If the IRTF and IETF follow this, we have RFC 7776, anti-harassment. The Ombuds team is available if you have any questions or concerns either about this policy or anything to raise regarding it. Next slide, please. As a reminder, this is the IRTF, not the IETF. We're very closely linked, but the IRTF focuses on long-term research issues in parallel with the IETF, and we collaborate with them as well. As a reminder, the IRTF publishes informational and experimental documents, and the primary goal is to promote the development of research and collaboration and teamwork, exploring these issues that connect cryptography to the IETF. There's RFC 7418. Yeah. All right, so the agenda and slides are available here, the data trackers on this link. And here is our outline. We have a very packed agenda, so I'm going to try to speed through this intro. We've got 6 great talks about different, whether it's individual drafts or adopted drafts or new ideas. Is there any agenda bashing? Going once, going twice. Thank you. All right, so I'm going to do a quick overview of the document status. There's been one new RFC since the last IETF, which is Frost. So congratulations to the Frost authors for getting this through. Oh, yay, all right. There are no current documents in the editor's queue, but the IESG review, there are 2 things that we've been working on, one for a while, one for not as long, but the properties of AEAD algorithms is, if there's any last words on this for anybody working on AEADs, this is sort of a last call. And Kangaroo 12, the hash function extendable output function is also right at the end. There are no drafts in IRSG review, and there are 2 in the IRTF chairs queue. As a reminder, we have quite a few active drafts within the CFRG. So I encourage these authors to continue working on them, converse about them on the list. All of these documents are updated, and none of them are currently expired. We haven't adopted any documents recently, and there are no documents in adoption call, but we do have 2 expired drafts, pairing friendly curves and BLS signatures, and there's a number of inactive and archived drafts that were adopted in the past, but haven't been continued. This is a new slide. There's quite a few erratas for a lot of these documents. So what the chairs would like to do is invite folks who have expertise in these areas to take a look at any errata that is referenced that hasn't been resolved yet. And if you have a contribution or a confirmation of any of these would be appreciated. But in the next few weeks, the chairs are going to be going through and attempting to close or address all these. And there's 3 pages of them. So there's several drafts and also quite a few new erratas that have been raised since the last one. So including 7748, 8032, 8331, and new ones with respect to the 9000 series. So HPKE has quite a few. And on the third page, we also have 2 new ones for 9497. So any help with closing these would be appreciated. Next slide, please. Okay, this didn't update on my slide, my page, but we do have a crypto review panel. These volunteers are also heroes, along with our note takers. We have a current slate of members. Several of them are here as well. So thank you, everyone, for the contributions on the crypto review panel. And as a reminder, the crypto review panel not only helps out with finishing the documents here in the CFRG, but also is a resource for the IETF for asking questions or clarifying things with regard to how to safely use cryptography in IETF protocols. All right, with that, there's no agenda bashing. Let's kick off the first presentation.
There is only one revision, right?
Hi, can you hear me? All right. Yeah, so my name is Amjad, and I'm going to present on partially blind RC signatures based on the draft that's linked in the slides. It's a joint work with Scott Hendrickson, Christopher Wood, and Kevin Yeo. The names are in alphabetical order. Next slide. So over the course of this talk, I'll go over some motivation for blind signatures, partially blind signatures, RSA blind signatures, uh, give a high-level overview of RSA blind signatures, and how do we change them into supporting public metadata, and then go over some benchmarks for our implementation, and then talk about current status of the document and the implementations. Next slide. So blind signatures are variable motivated at this point. They are used in privacy pass and under the hood in Google VPN and iCloud private relay, in avoiding repeated reCAPTCHA solvings, and as an anti-fraud measure in private click measurement, and as denial of service defense in Tor, and so on. Next slide. So for partially blind signatures, they also have a fair share of motivation. Recently, there was a public metadata issuance draft adopted into the privacy pass working group, which depended on two token schemes that support public metadata. One is privately verifiable variant, which is based on verifiable oblivious pseudonym functions, which have a flavor that supports public metadata. And the second one was a publicly verifiable variant, which was basically partially RSA blind signatures, uh, the draft that this talk is based on. Um, Moreover, blind signatures, when you enable public metadata with them, they offer additional utility. For example, you can think of your tokens needing some expiration time, and you can essentially tie those expiration time cryptographically with the token if you enable public metadata. Um, Other than that, you can also do things like service multiplexing, where you can essentially, maybe you want the same signing key to issue tokens with different egress policies, and using public metadata, you can achieve that. Um, Moreover, you avoid the one key per public metadata approach, which can have drawbacks like you have to fix your public metadata choices ahead of time, or you have, or also like if you have so many keys for per public metadata, then key management becomes a headache in production deployments. Next slide. So for blind RC signatures, last year an RFC was adopted, was published based on the fact that it's a simple scheme. It has a one-round scheme with and the server token issuance is stateless, and it has widely supported public verification. So it's natural to think of standardizing the variant, the public metadata variant for RSA blind signatures. Next slide. So now I'll give a quick high-level overview of RSA blind signatures. Next slide. So for example, you have a client and a server in this diagram. The server has the public key and a secret key, which sends a public key to the client. The client wants to blind sign a message. Next slide. For that, it will use the blind protocol. It will take the public key and the message and output a blinded message and an inverse. It will store its inverse in its state and send the blinded message to the server. The server will execute the blind sign protocol, taking the secret key and the blinded message, and output a blinded signature to the client. Next slide. Now the client will run the finalized protocol, taking in the public key, the message, the inverse, and the blinded signature, and output a final signature. Next slide. So a couple of things to note here is that the input message is not directly blinded. It's first encoded, and the RFC suggested PSS encoding for that. Secondly, the signature is verified as subroutine of the finalize protocol. The finalize only takes the public key, so signature is like publicly verifiable, which is a good thing about this protocol. Next slide. So now I'll talk about partially blind RFC signatures. How do we change the scheme to that? Essentially, this is based on works from Abe and Fujisaki and Abe and Kamenisch in 1996 and 1997, respectively. We have an accompanying paper that is currently in submission, which sort of has the accompanying security proofs and security analysis of the scheme, along with other some minor things. Um, so, to enable this public metadata in blind signatures, RC blind signatures, we essentially add additional parameter to all the protocols, blinding, signing, finalizing, and verifying. We basically pass public metadata to them. Next slide. The main tweaks here, or the main core things here to note is that instead of input message just being encoded by PSS encoding, we augment the input message with the public metadata and then encode this augmented input message using PSS encoding. Secondly, you do not use a standard public key, RSA public key. You derive the public key using the public metadata. So here, this H function that takes the public metadata, there's a typo. It should also take RSA modulus n. So and for implementation ease, we use HKDF in practice. Now, the output of this HKDF needs to be co-primed to phi of n, where n is the RSA modulus. And in order to do that, we do two things. We use strong RSA modulus, which is a product of two safe primes of a certain size. And we make sure that the output of HKDF is size restricted according to the size of the safe primes. And also it's always an odd number so that it stays co-primed to phi of n. Detail of this is in the draft as well as in our paper. If anybody wants to take a look. All right, next slide. Other than that, we proved one more for unforgeability for the scheme, which basically means that if I ask the server for n tokens on message and public metadata of my choice, I cannot forge an additional token. And also unlinkability under the same public metadata, which means that if I ask the server to sign two blinded messages under the same public metadata, and then the server returns me those signed messages, and I run the finalized protocol on both of them and shuffle the results and send it back to the server should not be able to link back the final signatures with the inputted blinded messages that it received from me at the beginning. We also take care of domain separation, where we make sure that all the RSA moduli, we make sure that for the same public metadata and different RSA moduli, the output of HKDF will be different. So the derived public keys will be different. And then we also make sure that input to the hash function in the input in the message augmentation as well as in public key derivation are domain separated by using standard techniques like adding tags and stuff like that. And moreover, as the public key are non-standard sizes, we added an allow service section to the draft. Next slide. So a little bit about the benchmarks of the implementation. Next slide. So on the right-hand side of the column, we have the partially blind RSS signatures, which have like the blind and the finalized protocols hover around a millisecond, and the blind sign hovers around 4.3 millisecond. We have two implementations that are currently available online. One is in C++, and the other one is in Go, and I thank Chris Wood for providing that implementation. Next slide. And current status, next slide, sorry. Yeah, so at Google currently, this scheme, we are using it under the hood in Chrome IP protection project and Pixel VPN because it's publicly verifiable and it fit our bill there. And there's a third-party audit of the cryptography involved. It's unpublished, but it's available online if somebody wants to take a look. Furthermore, we have an academic paper that with accompanying security proofs and security analysis, which is currently under submission. And we put a ePrint out last year, but it's a little bit outdated, and we're planning to kind of update hand in hand with the submission. So it should also be available in a few months. The updated version, the outdated version is still there if somebody wants to look at it. And yeah, I guess the question becomes: is anybody interested in adopting this document? Yeah. Next slide. Next slide.
That's it?
Yeah, thank you.
All right, any questions or comments? We've got a few minutes for conversation. I know there's several related works that have been explored by the CFRG. Yes, Scott.
Extremely minor question. I thought I heard you say that the signatures were unlinkable by public data by the server. Did I hear that correctly?
So they're unlinkable. The unlinkability proof like assumes under the same public metadata you cannot link them, right? Because if you have two signatures with different public metadata, you can already distinguish them.
Okay, but doesn't the blind server need to know what the public data is to sign?
Yeah, that's what I'm saying. Like if your messages have different public metadata, the server already distinguishes them.
Oh, okay. So what you're
Yeah.
saying is that even if they have the same public data, the signer he still has basically blinded. Never mind.
Yeah, yeah, yeah.
Okay,
Under the same umbrella, they're
okay.
blinded. Yeah.
I misunderstood. Thank
No
you very
worries.
much.
Sophie?
Hi, yes, I'm Sophie from Google. Do we have any plans of making this PQC? Like, I think there's some lattice-based schemes that we could use instead of RSA. Do we have any work in progress for that?
I don't think we have explored that right now.
Watson, Akamai. My question is the security model just one more signature for each metadata? Or do we also want to say that you can't extract a signature for different metadata if you're only allowed to get signatures for a certain set of metadata?
Sorry, just to clarify, you're talking about the one more unforgeability.
Yes. I'm asking, if I'm allowed to sign under HMD1 and HMD2, should it be hard for me to get a signature under HMD3?
No, I think the security definition right now it like covers that case. Yeah. Like covers the case where you cannot forge an additional signature for any public metadata. Yeah. There's a from what I recall, there is an additional caveat here that I think the scheme probabilistically fulfills that definition here. Does it answer your question? Or
I think I need to read the paper and think harder. I'm just sort of thinking about the same thing that happens if you do PKCS 1.5 without that initial bit, where there's suddenly relations among the hashes that you can exploit.
I'm not understanding the question because of the noise in this.
We have a little bit of noise in here, Watson. Let's take this question to the list and also continue discussion about this draft.
Or I could actually try to interpret. I think I had the same question internally.
Scott, do you mind coming to the mic?
Okay, I believe this is a Watson's question. Is there anything to prevent, say, two metadatas from having one being the exact multiple of the other, like one metadata hashing to 7 and another one hashing to 21?
Oh, right. Okay. So we analyzed in the paper, we analyze exactly that case where you can potentially launch some sort of that attack. And it turns out that there are some safeguards around that particular attack. There's like the probability of finding those particular E's, because we also size restrict E according to size of the safe primes, and the size are large enough that the probability that you will run into that case is into 2 to the minus 70s or something, depending on the key size. Obviously, that changes depending on the key size. And secondly, if you additionally at setup, if you want to, if you know your public metadata set in advance, you could essentially sanitize your key in such a way that you know that this case will never come up.
Okay.
Chris Wood, question on process. Because the privacy pass document that depends on this is now a working group document, what do we think the plan is for this one? It went through an adoption call last time, but it was like, there was not a lot of support for it just because, well, not a lot of people chimed in, but it wasn't necessarily required at the time because there was no IETF protocol that was using it. But that has changed. So I'm wondering if we get more clarity on like what the actual next steps are. Because this, blocking IETF work on IETF work seems not quite right.
So there's going to be a meeting or a presentation on Friday about potential new processes around crypto dependencies within the IETF. And as of today, there's no change, but I would encourage this conversation to go to the list.
Yeah, but in general, I think we'll, as chairs, we'll be mindful of this, that there is a potential dependency and try to expedite. I see. SAG on Thursday, and then I. Thank you.
Thank you.
Bert.
Yeah, for the note taker, it's SAG on Thursday.
Bert, thanks very much to the chairs for this opportunity to present. I'm Bert Kaliski, and presenting joint work with Swapnil Sheth, Andy Fragley, and Joe Harvey. We'll talk about Merkle tree ladder mode at a high level, two things. Interested in CFRG adopting Merkle tree ladder mode as a draft. And then secondly, a more general question that I'll explain. Interested in CFRG working on modes of operation for signature schemes as an area to provide advice to protocols that are integrating some of the new post-quantum cryptography standards. So on to the next slide, please. So a year ago, Joe Harvey presented on this topic. I'll give you a high level of how we see Merkle tree ladder mode. What you'll see here is a collection of 3 trees that can be used to authenticate 14 nodes. The first one has 8 nodes, the second one has 4 nodes under it, and the third one leaves 4 leaves, and the third one has 2 leaves. And this, in some places in the literature, is called a Merkle mountain range. There are a lot of people that have arrived at this kind of construction. We're using it particularly for an evolving message series when it's expensive to compute the signature. So the use case that we focus on in our research is DNSSEC. If you're continuing to expand your zone and add more records, it's convenient to be able to organize those as leaves of a Merkle tree. And as you add more, you get more internal nodes. And we structure those in what we call a ladder on the left-hand side. And the ladder has rungs in it. So think of the rungs as the designations of specific nodes in your Merkle trees or in your Merkle forest. If you sign all those rungs, you can then authenticate all the leaves. And the goal is to have some stability as the Merkle tree forest evolves so that you can reuse old ladders when possible. I'll take that as a short introduction. If you want to take away something simpler from this slide, just think in general of using Merkle trees to authenticate multiple messages with a single signature on the root of the Merkle tree. We would call that a mode of operation. It's a way of using the underlying signature scheme to be able to authenticate multiple messages with a single use of the signature. Next slide, please. Joe Harvey presented a year ago, IETF 117, and there were 3 next steps. Request to review the draft. We were planning to release an open source library, and then we plan to publish a draft on using Merkle tree ladder mode with DNSSEC. We've done all 3. Next slide.
Can you move a little bit closer to the mic?
The Merkle tree ladder mode draft has been updated based on feedback and evolution of the post-quantum standards from NIST. And we had a hackathon at 118 on the Merkle tree ladder library, and version 3 of the Merkle tree ladder mode draft just published now aligns with the way that NIST is approaching what we would call modes of operation. So for those of you who are following the NIST PQC discussions on FIPS 204 and 205, you'll note that NIST has introduced a pre-hashing variant plus a pure signing variant. I assume many of you are familiar with that. You've seen the mailing list discussions. So in order to support applications that want to reduce the operational impact on the underlying signing process, there's a pre-hash mode. You hash the message and then put it into your underlying signing. That's attractive if your underlying signing is in a hardware security module, and it's particularly important for schemes where you make 2 passes over the message. And for instance, in Sphinx Plus, you hash once to get the randomizer, then you hash again with the randomizer. So now if you have a multi-megabyte file, you have to send it twice into the HSM, assuming the HSM can't remember what was sent in the first time. So the pre-hashing lets you do that outside, or maybe 1 pass of sending it in to do the hashing. So as I show on the slide, NIST defines pure hashing as a way of formatting the input to the underlying signature scheme, prefixing it with a 00 byte, and then that's followed by an optional context string. If you prefix with a 01 byte, that means that what's going into the underlying signature scheme has been pre-hashed. So pure, just directly the message, pre-hash, the message prepended by a 01, object identifier, context, and so on. There was a lot of good discussion on the NIST PQC mailing list about the pros and cons of this approach, and including a panel discussion that we participated in at the NIST PQC conference in the spring. I'm not sure what the final outcome will be when the NIST 204 and 205 are published, but seem to be leaning in the direction of supporting these. But if you've followed the discussion, you know that there's some important trade-offs going on. Should the FIPS themselves specify both of these modes? Would an application use both of these modes? How do you distinguish between these modes? And these are general questions that come up even as recently as Falko Strensky's attack on PKCS7 and CMS. If you remember what was taking place there, you had either a hash being directly input to the underlying signature or an authenticated attribute structure where one of the attributes was the hash. How do you distinguish between the 2 of those? So one way is to distinguish cryptographically, as NIST has proposed, a 0 or a 1 before a structure so that you're never signing something that's ambiguous in its interpretation. Another way is in your application, only use one or the other modes. A third way is for specific key to say this key should only be used one way or the other. So you leave it to key management. Well, that's related to the general question when you're using a key. What is this key used for? Because a key can sign anything. How do you interpret the thing that's signed by the key? If you change the context of the interpretation, something that's signed meaning one thing is now in another language, or it's in another format, syntax, and so on. In the discussions that I followed on the NIST mailing list, the general sense I got from those who didn't want to see the 0 and the 1 byte put into the standard was let protocol designers figure out how they want to use this. Let them distinguish between pure and pre-hashing and something else. Well, that feels like it needs some guidance. So whether NIST standardizes on 0 and 1 or does something else, it's good to have some guidance to protocol designers who are thinking about using signatures in multiple different ways, sometimes hashing beforehand, sometimes not, or other modes of operation. Just elaborating on this a bit more. And in our comments to NIST, we said for the pre-hash mode, the pre-hash exactly does that. It hashes only. Depends on collision resistant. Now, no doubts about collision resistance, whether that will be secure, but we have history that suggests sometimes when you assumed collision resistance, later on that didn't prove to be the case, and some randomization was needed to protect you against the predictability in advance of what was going to be signed. That was the SHA-1 story. There's no input in this in the 0-1 case of the public key that's being used, so any collision then is universal, can be applied to anyone who's doing the signing. Those feel like design considerations for additional modes of operation. If you wanted one with randomization, one with public key input. That's a long way of expanding on that bullet. But that's the motivation for saying Merkle tree ladder mode is an example of a family of ideas. A family of how do you use this underlying signature scheme that's being standardized, as powerful as it is, in different ways, pre-hashing or hashing multiple messages together. How does that evolve over time? So we followed a similar technique with the latest draft of Merkle tree ladder mode and decided to reserve the values 80 and 81 hex, figuring they were far enough away from 0 and 1 that they might not be reserved. There's no reservation scheme for that yet, but we wanted to be visibly distinct from the 0 and the 1 if we're using the underlying signature scheme and the input is the hash of a Merkle tree ladder that represents multiple messages. Okay. There's more details in the draft around that. We've also released the open source software implementation, and if we go to the next slide, and an internet draft on using Merkle tree ladder mode with DNSSEC. If you were at Hot RFC or at the hackathon this weekend, you saw we were demonstrating an initial use. We have a zone file that's up and running, and when you look at the zone file, you'll see that one of the signatures is very long. It's a SLHDSA signature on the Merkle tree ladder that represents the whole zone. The rest of the signatures are short. They're more in the size range that you'd expect to see for DNSSEC signatures running over UDP and so on. Okay, next slide. Just a couple final points here. So previously disclosed the same statement. VeriSign has announced public royalty-free license following IETF note well and so forth, and you can find the IPR declarations for that. And then final slide. Our request, would CFRG be interested in taking up MTL mode as part of researching modes of operation in general? The MTL mode document has a lot of materials in it right now because we wanted to be as complete as we could and how it specified how it works with different underlying techniques, security considerations, and all those kinds of things. But the larger question is, how do we think about modes of operation for signature schemes? I think it's important with the arrival of the pre-hash versus the pure mode, with the size trade-offs that are unprecedented in terms of the operational impact, and additional understanding of security proofs. This feels like the right place to pursue that further. On the DNS side, we're continuing to work on the DNSSEC use case, and obviously we're open to other use cases as well. Thank you.
Okay, you mentioned that you were extending the prefix bytes to include 80 and 81. I believe that the NIST API will also include a domain separator. Would using that, setting that to a specific value, serve the work just as well and stay within the NIST API?
Good question. So the 0 and 1 bytes as well as the 80, 81 are part of the domain separator. So the NIST domain separator is 0 followed by context, or 1 followed by OID followed by context. So
okay, maybe this is context then, but that's what I meant. You have context is freely submittable, settable by both the signer and the verifier, I believe. Quinn, am I remembering that correctly? Yeah, the context within the signature verify APIs.
Please come to the mic for conversations.
I think I understand the point. The domain separator has the 0 or 1 at the beginning,
Okay.
context, optionally the OID.
Yeah, I was
Yes.
thinking.
Yeah, we could use the context, and this is all flexible, right, as we're defining it. The reason that we adopted the 80 was to be visibly distinct from the other ones because NIST has already defined what the 0 and the 1 looks like. 0 is pure hash, 0 and 1 is pre-hash, requiring a hash function. So we did something different. Go ahead.
Quinn Danganis, I don't remember exactly the values for each of them in my head right now. But you know, listing numbers for listing functions, that what the purpose is, right? Yeah.
But I thought that basically whenever you sign, whenever you verify, you got to select a context. Yeah, and my point was you don't need to extend, basically introduce new ideas. You can do the same thing with existing ones.
Yeah. Okay. I think that's a good follow-up discussion with NIST on the intent of what the 0 and 1 prefixes mean.
Okay.
But I'm open to that system. But it's an excellent point on interpretation. But then think more generally. If there were other modes of operation, how would you specify those? Would it be different bytes, different context, and so on?
Hi, Russ Housley. Hi, Bert. Yesterday, a new mail list was created about post-quantum signatures in the DNSSEC context. I think that was started by one of the security ADs. And this technique looks very interesting in that context. So I'm really excited to see this group pick it up.
Thank you, Russ.
Thanks, Bert.
Thank you.
Hi, this is Rüdiger Geib. Sorry, my camera could not be activated. And yep, I'm presenting draft IPPM capacity protocol in here, the crypto options we choose. I'm with Deutsche Telekom and I'm not a particular security expert. So I'd be grateful if the note taker or the chairs are helping me if there are comments which I have to work on. That would be really great. The SecDay early review we got was made by Brian Rees, and that took a while now, and we solved all comments, and by now he asked us to please present our crypto approach in the CFRG, as he's not aware of any other implementation which shares the approach taken by us. So what we do is we use 256-bit HMAC SHA-256 auth digest for authentication. This is completely standard conformant. And what is special about our approach is if authentication is combined with encryption, we specify that the second half 128 bits of the HMAC SHA-256 auth digest is used as initialization vector for the 128-bit AES minus CBC encryption. All right, what we did so far is looking for standards which say this is either a bad idea or this is feasible. And the properties required for a CBC IV following NIST SP 800-38A, the IV must be unpredictable. Now, we believe that the result of the HMAC meets the unpredictability requirement. But Brian asked us to look for confirmation or contradiction, of course, if that is correct. So the key to the HMAC is unknown to an attacker attempting to decrypt the message. And the output of HMAC minus SHA-256 is a uniformly random value. So that is all I can tell you, and that is all I've collected. And I saw that I get quite a lot of time for discussion. So please, if you have to make statements, start now.
Hello, Watson Lad Akamai. It sounds from the description that you're taking the HMAC of the message, then using that as the IV, and then CBC encrypting the message. This is not the security properties you're asking for with encryption aren't just can the attacker decrypt. Because of the CBC, you have to put in padding. There are padding vulnerabilities that can be exploited unless the encrypted message is authenticated. And so you have an issue with that.
Yeah, as I mentioned, I suggest you to take notes, and so I can get that written and then see how to work on it. I'm not a security expert. I don't start to discuss this. It will be a shame for me and annoying for you.
Jonathan Hoyland, Cloudflare. So this isn't unpredictable at all, because if you send the same message twice, it'll be encrypted. It'll get the same HMAC, which means it'll have the same IV. So it's definitely not unpredictable.
Well, the HMAC, how big is the probability that an HMAC appears twice if the content of the message starts to change?
100%. It's deterministic. It'll do the same thing twice. Why? Also, Mike.
On the mic.
On the mic, please.
Deterministic encryption is not an issue. The vulnerabilities for CBC mode encryption come down to encrypting different messages. If you just encrypt the same message twice, well, quite frankly, if the attacker wanted to, he could present the same message twice to the receiver and to do whatever evil thing you were expecting him to do.
So the question on the slide is this unpredictable? And my answer is no. Whether that has other vulnerabilities is the answer to the question on the slide is this is not unpredictable.
There is actually a mode that has an RFC that does exactly what you want, which is called AES-SIV. It uses CTR mode instead of CBC mode. Otherwise, it is very similar. It doesn't use HMAC, it uses CMAC. But if you want something that is a deterministic authenticated encryption mode, use AES-SIV. I don't know what RFC number it was, but you can look it up. Yeah, I don't know. That will not be vulnerable to like padding oracles, and that has like a ton of security research behind it. It's a good mode. It has an RFC. Use it. It will solve your problem.
Okay, we've cut off the queue. Thank you so much for bringing this here. It would be great to have a cryptanalysis session in this room, but it might be preferable to do so on the list going forward. And we do encourage groups who try to put together new security mechanisms to get them reviewed through the CFRG. Mailing list is probably the first step.
Yeah, it would be great if the note taker has been picking up everything which has been said on the micro, because that would be really helpful for me. So then thanks. And
okay, we'll make sure to update the notes from the transcript in order to have a complete
all right,
outcome for you. Thank you.
Thank you. Bye.
Hi, Shay. Hi, Shay, you're on.
Hello, everyone. I'm going to talk about a mode of operation that uses AES-GCM, which is called double nonce derived key GCM, and in short, DNDK GCM. So next slide, please. First of all, here is a slide to indicate what limitations of AES-GCM we see and what are our goals. So on the right-hand side, I'll just skim through this. Short nonces, 96-bit nonces, if they are randomized, they would collide after so many times. And if you want to keep the collision probability of the nonce, which is a catastrophic event, to be below 2 to the minus 32, then you need to abort the key, rotate the key after 2 to the 32 times. And this is a very small amount of usage for a given key, certainly in a cloud encryption environment. The other limitation is the birthday bound, right? Here we are using AES with 128 bits. You can, this is a small calculation, if you want to keep the distinguishing advantage below 2 to the minus 32, you cannot encrypt more than 2 to the 52 bytes. And last but not least, there is no key commitment. It is easy to find, maliciously to find the two keys such that, and the ciphertext, one ciphertext that would decrypt properly under two keys. So on the left-hand side, these are our goals: to encrypt at least 2 to the 64 bytes, to use random nonces. So you see, this is not possible to do right now with AES-GCM. The security, to use only a single security assumption, basically that AES is a pseudo-random permutation. This is something everyone believes. To enjoy some kind of a NIST compliance umbrella by claiming this is not really a new mode, it's just a way to use AES GCM and bypass the limitations. We want, of course, good performance. We want to also get optional key commitment and minimum effort. So we want to be able to leverage all the software base, hardware base that we can find and leverage the same code. So next slide, please. So a derived key mode is a general concept. Actually, it is already being used in AES GCM Civ. And basically it says you take any kind of an AEAD, input nonce, additional data and the message. You start by deriving new subkeys from the nonce. So you see, okay, this should have been some kind of an animation, but it collapsed. So you take a root key, you apply some kind of a PRF to the root key in order to derive a new session key, and also a key commitment value if you want this. And then you are using the derived key with the underlying scheme and just apply this. So basically it converts a mode into a multi-key scenario where hopefully every key is being used only once and no collisions on the keys. So, and then you'll ask, what nonce are you going to use with the underlying scheme, and how long is the nonce? So we are going to separate them. These are two different questions, and basically we're going to use the fixed nonce, take all zeros, and the nonce for the compound scheme would be long. So next slide, please. This next slide. So how long should the nonce be? So this is just a very quick computation. If we want to use it for 2 to the 64 times and have collision probability below 2 to the minus 32, you can see that you need at least 160 bits in the nonce. We're actually taking more. We're taking 192 bits. But here is the challenge. It is longer than the block size, that the underlying block size of AES. So how are we going to accommodate this? Next slide, please. So this, oh no.
I saw this just half an hour ago. I didn't let you.
All right. So okay, we will say in 192-bit nonces do not collide after 2 to the 64 times. I mean, the collision probability is very small. If you derive 256-bit keys, they're also not going to collide, and you cannot do some kind of offline guessing on the thing. So you can see now that double nonce DNDK GCM is actually a selection with 24 bytes nonce, deriving 256-bit keys and using a fixed nonce of all zeros, 12 byte zeros, with the underlying AES GCM. So the idea, nonce are not going to collide, derived keys are not going to collide. we are using only one assumption, well, it's only one primitive, which is a yes, but we still need some kind of a beyond birthday bound PRF in order to do the derivation. Because we cannot take just something, just a standard PRF, because it's not going to sustain 2 to the 64 times. So we need the beyond birthday bound derivation based on AES. Next slide, please. Okay, I don't know. So basically, the idea is to take a long nonce, split it in 2 halves. Each half would be shorter than the block size of AES, 128 bits. Apply some kind of beyond birthday bound PRF, and then XOR the results. And miraculously, this works. This gives you a beyond birthday bound PRF. Now we can use, if the 2 halves of the nonces are shorter than the block size, we can easily use AES. Okay, next slide, please. So here is actually a picture of how it works. We start with 24 bytes, split them into 2 12 bytes. Now we feel safe. We have 4 more bytes that we're going to 3 bytes are going to be used as a configuration. You see, this is the configuration. On each half, we're going to apply XOR-P permutation in order here to derive 512 bits. So to do XOR-P, this means that you need to do 5 independent AES calls on each half, totaling 10 of them. And then you XOR the result, and you have the first half would be the fresh derived key. The other half would be a key commitment string. Okay, so now what happens if you don't want key commitment? Of course, you don't want to pay 10 AESs, right? Because many usages don't need the key commitment. So next slide will show you this. So yeah, do the same thing, just don't do 5 AESs with the XOR-P, just do 3 on each side. And here is you see that there is a different config string. The reason is that we want that if we don't want the key commitment, we want that the derived keys are going to be different. So with this type of a domain separation between the 2 cases, we're going to get different derived keys and different key commitment in the previous case and no key commitment here. So if you are sending a message and your intention is to have key commitment and somebody drops it, it's not going to work because the key derivation is not going to be consistent. Next slide, please. Okay, a warning. Is it also possible now to use the 192-bit nonce just as a counter? The answer is no. Well, because you can just do some kind of manipulations and get the dependencies on the underlying blocks. So if you really want to use this mode with a counter, you need to for example, you need to freeze half of the nonce and then run a counter, a 96-bit counter on the other half. This would work. Here is the question: Are we sure we want to use this mode with a counter, with a counter nonce? This would be a little bit wasteful because you're using only half of the nonce. But it is possible. Next slide. So there are 4 variants right now. So with config that is all zeros, this would give us a standard AEAD interface because there is no key commitment and it's just the standard AEAD. If you configure it with 1, then we have key commitment. And now we can also have 2 versions of a counter, a half counter option with and without key commitment. So basically there are 4 options right now. Next, please. So okay, you can see how it works. We have the general framework of the derivation. We can use it with and without key commitment, and with random nonce or with the counter nonce. And we have all of these options. They are actually controlled through the configuration 3 bytes. And okay, next slide, please. I don't believe this. All right. So performance. We said we want something efficient. So this is the performance on a short buffer. I'm comparing to OpenSSL. OpenSSL is slow because of different reasons, but we have our own optimized AES GCM and optimized. It's called haberdashery. It's a library optimized DNDK GCM. So we see that there is some difference on short buffers. This is because of the overhead. Next slide. So now we have a medium buffer, like a 1 kilobyte. So you see that the differences decrease. Still OpenSSL loses because the key setup is very slow in OpenSSL. Next slide, please. A long buffer, 16 kilobytes buffer. You see that this is almost the same, and this is exactly the idea, that asymptotically, if you're processing a long enough message, then the overhead is amortized and you get almost the same thing. Now OpenSSL catches up. And the next slide. Okay, this is the asymptotic. I took a 1 megabyte buffer, so you can see. So you have some overhead if the messages are very short. And the difference between DNDK GCM and AES 256 GCM becomes smaller and smaller. Asymptotically, it's the same performance. Next slide, please. Okay, so if you want details, where can you get code? Optimized code. There is a library that we call haberdashery. It's open source, high performance assembly implementation of many things, several things, including AES 256 GCM, AES GCM Sieve, SievMac. This is a kind of a Mac scheme, and the DNDK, so you can get it all and compare. There is a Git repository. If you want more information, there is a talk that I gave at Real World Crypto. So you have the video and the presentation at the NIST workshop, another presentation. And there is also an internet RFC draft that I'm going to actually update after this session, but there is already a definition. And now next slide, please. This would be the last slide. Well, the last slide is a thank you, but one before the last slide. Here are a few questions that I brought to discuss. So remember, we have the double nonce is 24 bytes, deriving 32 byte keys, a fixed nonce. Well, actually, this defines everything, and double XOR-P derivation. So is it reasonable to support all 4 options? I can certainly sympathize with 2 options, which are with key commitment and without key commitment, because of course you can always say we only have one mode. It always gives out key commitment, but you can ignore this. But then this is wasteful because you're using 10 AES calls for the derivation, whereas if you don't want a key commitment, you can do it less. So the first 2 configurations, first 2 options actually are a reasonable choice. But now the next question is, should we allow or support also the use of a standard counter nonce with this construction, with and without the key commitment? And if we do this, which is a better option? I mean, you have to freeze half of the nonce. Otherwise, you can do some manipulations and the security proof doesn't work. So there are two choices. Right now, I'm writing the RFC with the first one, where you have all ones on the on one half, and then a counter, because this jumps into your eyes, and you see immediately if somebody is trying some kind of a manipulation with this counter mode, and then you can immediately reject. But it might as well be like a long counter that starts from 0 and whatever, and it would never spill over. So you can just zero this half. It's all the same from the viewpoint of the security proof. Should we allow to use different configurations with the same root key? Okay. Or a root key would be defined together with a specific configuration. That's another question. Now, output format, should it be ciphertext concatenated with the tag and concatenated with the key commitment, or the other way around? And in general, should we worry about different parameters, because we can use a shorter root key, for example, 24 bytes, like 192-bit root key, and shorter derived keys, shorter renonces, and we can actually commit with a shorter key commitment string. But of course, once you add these, you get an exponentially large number of options. And in general, I hate options. I want the smallest amount of options. So these are the questions for discussion. And the last slide, next slide, please. This is the thank you. Okay, you see? Okay, so thank you very much. And I think that the queue there, so Daniel first.
And there are PowerPoint version of your slides uploaded, so if people can have a look later, they can see animations and hopefully
Okay.
So.
Something was messed up with the PDF conversion from, yeah.
Thank you very much for the talk. Listening to your use case, it sounds very much like the use case for tweakable block ciphers, which there are a number of bits of research into. But your method, unlike tweakable bits block ciphers, require recomputation of the key schedule, so it sounds a bit less efficient. Is there a reason you're not going for a NIST-approved tweakable block cipher to prove?
Well, basically, I wanted to use the general framework that is already used in ASGCMC, where you have a derivation. It's a general concept. You can apply it to anything. And most importantly, I actually wanted to run ASGC, the classical standardized ASGCM under the hood. So without making any changes to that standard, and in a way to say this is a way to use AS256 GCM. You just use it in a way that every time you encrypt something, you are using a one-time key, and the key is being used only once.
Okay.
Martin Thompson, this is very interesting. I particularly like the idea of being able to use the one input key basically forever, which is one thing this would provide.
And the random knowns, I mean.
Right. So I do think Daniel's concern here is one that I share. The applications that I'm thinking of would very much benefit from being able to avoid the overhead on a per message basis of having to manage the new key each time. To give you a bit of color on this one, we have a lot of people who are looking to use TLS over very, very long periods of time, and want to avoid some of the complexity of the rekeying that's going on there. And so if you can avoid having to rekey by having something of this general shape, then there's a possibility that you can avoid some complexity in the protocol.
I don't know.
Right?
I cannot change the whole concept on the fly, but this I just can tell you that the whole overhead with the 10 AES is 175 cycles.
Right. It's not a lot, and maybe that's not a big deal. On your question about do people want to put in a counter nonce on this one in that application? Yes, they very much would. And they would probably like to do the same sort of thing that TLS currently does with its nonce, just on a larger scale, and XOR the counter in with the thing. Would that work in this case? I suspect it would.
I don't see a reason why it wouldn't work.
Right.
And by the way, I forgot to mention, if you're freezing half of the nonce, then you can do the left-hand side derivation once and then apply this. So this would be just XORing some fixed string. So this is a waste, but this is the cost of trying to use this construction with a long nonce and the counter.
Yeah, and so in that context, having key commitment is not particularly interesting, but there are other contexts where the key commitment is very interesting.
Yes, and this is why I built two options. In most cases, you don't really care about commitment because, you know.
All right, thank you.
Thank you very much. Yes, we're done. Okay, so thank you very much, and I hope you post the good version.
Yeah, both versions are available on the data tracker. All right, Stephen Farrell.
So this should be, well, this could be quicker or slow, I guess, we'll see. There was interest in chems and combining chems for various reasons. The chairs formed a design team. We had a bunch of calls. Next slide. The people who could make the calls are listed here. Next slide. So I just want to check how many people kind of saw the mail to the list and kind of read it. Okay, not that many. Okay, so basically the design team, we had a bunch of calls. We were basically not asked to produce a way of doing chem combiners, but to try and figure out requirements that the research group might address. We looked back through the list discussions. There's valid and conflicting requirements. Looks like a single answer is not going to solve everybody's use cases. There's a bit of a lack of clarity about some of the security properties we might want, and there's lots of choices. And some people want to get this done soon. Next slide. So the next slide, the output is the following that we mailed to the list a few weeks ago. So first, basically the design team recommends that the research group might want to produce a document that has the following bits in it. So the first part is basically identifying which security properties are IETF relevant. There are papers that have specified like more security properties that you could have here. It's not clear that all of those security properties are relevant to an IETF context, and there's just so many it's confusing. So a bit of text that kind of clarifies that and other kind of issues to do with using them. Next slide. And then the second one is to provide, the second part we'd like to see in that document is to provide an overview of kind of ways you could do this. And then to have some concrete combinations that are justified that way. So next slide. And the design team figured that these are the set of things, the set of combined chems or hybrid chems that would make sense to define in a first instance. And so include the definition for those in the document with some pseudocode, etc. Next slide. And basically, there's two at about the roughly 128-bit security level and one higher. If there was no need for the first one, which is the P256 one, then the design team said it would make sense to omit it, but we thought that probably there is some people want it. And there are other kind of things people would like to do. And the design team figured doing those three listed first and then doing other stuff later would make sense. And I think that's it, is it? Is there another slide? Yeah. Okay, so I think if the research group were happy to proceed on this basis, then they'll be back over to the research group chairs to go find some victims to write the documents. And the rest is just time for people to say, that's terrible, that's okay, we're happy, we're unhappy, or whatever.
Hi, I'm Deirdre. I was on the design team. I think we should do this, and I volunteer as tribute to help write the document.
Chris Wood, I also think we should do this. However, I don't think step C should be in that same document. I think it would be useful and advantageous for us to pull the actual concrete instantiations out into separate documents, because that's really the important part here. We want to get things unblocked for HPKey and TLS as soon as we possibly can, and trying to gate all of that on something that's more general purpose, more researchy, it feels wrong. So I would strongly suggest that, like X-Wing is today, keep it in a separate document, get the code points based on that, make sure it's consistent with, you know, whatever the good vibes are in the other document. But please do not hold up the code points on a research document.
Okay. So just to summarize, you're okay with the kind of content, you just wanted separate documents?
Yeah, correct. Good. Because like I only care about that actual instantiations at this point. I just want to be able to go to the registries and be like, can we please get our code points? We know what we need for HPKey. We know what we need for TLS. Let's just make that happen. For the other applications and other protocols that want to use chems and might depend on different properties, yeah, that's going to require some of the work that's laid out here. Like we're going to need to figure out what those actual protocols require, what sort of binding they need. And it's perhaps a bit premature to allocate code points for those use cases, but we know exactly what we need for TLS and exactly what we need for HPKey right now. So let's get those
I saw a couple of people nodding as Chris was talking.
What? Yeah, I mean, encrypted client hello uses HPKey, which requires only an CCA2 secure chem, does not require anything beyond that. Okay.
There's some chat about encrypted client hello. Any other feedback? Are people generally happy? I guess I presume it would be useful for the chairs if maybe you could do a poll thing and say, does that poll thing work?
Okay. Watson first, but
Watson has a question.
Watson,
but, yeah.
Sorry. Yeah,
Watson and Akamai, I'm glad that we've concluded this and have a plan to write the thing. I agree with Chris that we should try and organize it so that we can unblock groups as quickly as possible, even if there's some more contentious things waiting in the background. We really are seeing people want to deploy these on very close timescales.
Okay. Paul?
Paul Hoffman. I was sort of one of the people who got this going on a private message that with the chairs and such. I'm perfectly happy to have it be separated. There's no reason to slow anyone down with where they're going. I disagree with what Watson just said. I don't think that many people are on tight time frames. And so doing this right, getting these sussed out might take a year or two. There's going to be plenty of time for people who aren't almost already there, who are thinking about later applications that need chems, to then look at this and go, oh, this is how we want to do it. So I think it would be great to do this, separate things out, let people design from the base document.
So did you want to, the poll question is, are people happy with the proposed CAM design team plan?
Yeah, modulo, I guess modulo Chris's comment on
given how few people read it. Well, I can still ask.
Okay, so can we also just have a raise of hands again, like who has read the output of this email?
Okay, it's more than the last.
Okay, so that's more than before. So
Keep reading,
so we can actually
reading.
have.
Shall we delay the session so more people can catch up?
I think some of the questions at the line there reflect a tension between having a code point versus having what our CFRG is supposed to do, is generating research documents and recommendations. So I would encourage that tension to be fleshed out. This is not a bring your algorithm and get a stamp code point group. So that may be a reason why splitting it out is not in line with the processes of the CFRG.
If I may comment on that, the CFRG and the processes do not require this group to bless anything for HPKey or TLS. The registry and the registration policies only require a stable internet draft and then review and approval by the experts. So we could literally just take X-Wing today and go get code points. We don't want to do that, but I'm saying like it just does not need to go through the CFRG to RC.
publication comes with some expectation of stability that some of us might prefer to rely upon. And so if we took a draft and grabbed a code point and started deploying things, there is, I guess, heightened risk that this group or some other in the process of working through publication would change things in ways that would cause interoperability problems. So the preference, why are we allowed to do that? That's a long discussion that I'd prefer not to have in this, but we can take it offline.
Rich.
Yeah.
Yeah, one of the TLS registry experts. We already have a Kyber draft 0 is one of the registered code points, and yeah, for changes, we can talk about it offline, or you can examine the IETF history. I think splitting up does make sense.
Does or does not?
Does.
Does.
Sorry.
Okay.
I should close the poll.
Just a
So the poll says 22 yes, 0 no, and 10 no.
Okay.
23 yes.
Okay.
Does this question account for the split or not?
I assume this includes the idea of splitting.
It does include
That's
split?
my assumption, yes.
Yes.
Okay. Great. Well, add 2 more to the yes then for me, Mark.
Okay, so yeah. Well, yeah. Okay, so my conclusion is people are not unhappy, and I guess it would be confirmed on the list. I think.
Okay, and is there anybody else who would like to volunteer as a co-author with our wonderful volunteer? We can bring that to the list, and the chairs will assign.
Yeah, I'd be willing to help do something. Okay,
thank you. Steven volunteers. All right, let's do the last one. Yeah. Just 1 second. I'm loading it up.
Okay, this is a rough sketch of some ideas that may motivate a possible look at a HPK v2, or however we do v2s in CFRG. I know in other working groups in the IETF, they do things like BISs and blah, 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 but just a bunch of ideas that motivate like a bit of an overhaul, because we have a couple of ideas. Next, please. So I was here, I don't know, last meeting, the meeting before that, discussing how if we want to include any new chem in HPKE that's not the written into the document DH chem, we lose a lot of binding properties that are already guaranteed by DH chem, or at least we lose the guarantees of binding properties that we get by using DH chem, which is the one that is deployed in basically all deployed instances of HPKE v1 nowadays. That means that you don't have a guarantee that the public key that's being used in HPKE is bound into the shared secret that you're actually using to do your actual encryption. You don't have any guarantee that the ciphertext or the other ephemeral public key in the case for DHChem is bound into the actual key that you're using to do these things. And this opens you up into re-encapsulation attacks or other kinds of attacks that you don't have to worry about with DHChem, the current only cipher suite we have defined for HPK v1. HPK v1 also does not define a signature-based authchem. It's all DHChem authchem modes. And if you want to do something in the future where this is hard to do with post-quantum variations, we don't really have an option for that. And third, we don't have a way in HPK v1 to mix in multiple rounds of encapsulation or auth encapsulations or having multiple pre-shared keys into it. There's just like one go. You have a one shot, or you just have one round of whichever mode that you're doing, base mode, auth mode, or using pre-shared keys, and you're done. And if you want to do anything more complicated, that's all at the protocol layer, and you're sort of doing a nesting doll of HPKEs. It's not built into the thing. Next, please. So to fix the binding issues in a new version of HPKE, we'll call it HPKE v2, in a backwards compatible way, we basically force all the chem cipher suites that use HPKE to do all the binding stuff that we do for the DH chem variant for all the variants. So if you have a chem that defines encapsulation and decapsulation, like MLChem, like X-Swing, or your favorite variant of a hybrid or non-hybrid chem, you will define a new encap with binding, or we do it for you, where we do the encapsulation against an encapsulation key, we serialize your encapsulation key, we create a chem context where we have the encapsulation, the ciphertext of the chem, not the whole HPK ciphertext, and your serialization of your public key. And then you have the shared secret from your encapsulation, the whole chem context, which includes your public key and your ciphertext, and use that to derive your shared secret that you're actually using to do your HPKE encryption at the bottom layer. And then the other side is basically doing everything the same thing to actually compute the shared secret, where you're binding to the public key and you're binding to the encapsulation key and you're binding to the ciphertext with the shared secret from the encapsulation. Fully backwards compatible with DHChem and HPK-AV1, and the same thing can be done in the auth encap and auth decap mode while also binding the sender's public key. So we can get that too. Next. Fix 2 is actually including a new signature-based auth-chem mode. So this includes your signing key and your receiver's encapsulation key. And so we're basically doing, if you have a chem that has encapsulation and you have a signature scheme that gives you keys and gives you signing and gives you verification, you do your encapsulation as before, you serialize your public key, you serialize your signing key, your verification key. And you can cat all of the ciphertext, the encapsulation ciphertext, the chem public key, the signing verification key, smush all that together, and then you sign that with your signing key, and you can concatenate your encapsulation ciphertext and your signature, and then you derive your shared secret for the whole actual HPKE from the shared secret of the chem and that whole ciphertext, which is also over the signature and also all the signing key material. And then you do everything the same on the other side. You just verify the signature before you actually finally compute the shared secret and output the shared secret. This also helps to mitigate these key compromise impersonation attacks that are not addressed in HPK v1 at all, by including a special one-shot mode where we can include the hash of the payload as well into that SIG chem context where we're computing in both phases, and this is also included in the signature, and would prevent some of these insider weaknesses. Next. Cool. And then the third thing is making more generalized key schedule to allow multiple numbers of endcaps and multiple numbers of possibly auth endcaps if you wanted to. We allow you to be repeated any number of times so that you can incrementally construct and bind a context that includes all of the elements of the endcaps that we're actually using. And if you think this sounds a little bit similar to some of the TLS 1.3 key schedule, you would be right. The advantage of defining this combination inside HPKE would that we could allow people to combine any number of PQ and non-public key chems, signatures, and pre-shared keys in one-shot HPKE construction, as opposed to kind of putting it outside and leaving it up to an external protocol to figure it out. In practice, people likely want at least one, at most one Diffie-Hellman, one post-quantum chem, one signature, maybe one post-quantum signature, or sorry, one traditional signature and one post-quantum signature, and maybe one pre-shared key. But even that's a lot, so a generic composition may have value. So next. Yep. So this is a bag of stuff. Do we want to try to write something up and just be like, hey, this is like a stab at HPK v2? Should we try to break them up into extensions and each one of them be its own thing? Each of these requires a new security analysis. I know that Karthik and Franciscus are interested in spearheading those. Although because they're backwards compatible, we can reuse a lot of proofs for HPK v1 for the pre-existing DHChem case. So it's not like starting from scratch. We're able to reuse a ton of stuff. That's about it. Like thoughts, feelings. I hate it. I love it. Yeah.
You have a fast-growing queue. That's why I was making noises.
What's that?
Fast-growing queue of people.
Oh.
Yeah, we've got only 5 minutes left, so
Yeah.
let's lock the queue. There's 6 people in it.
think that's
7 now.
Chris Patton. So I would be supportive of cutting a draft with fix 1.
Okay.
I don't think we should. I don't think we should be doing auth chem. I think there's certain protocol details that are fine to be left to the protocol. So yeah, that's my opinion.
All right.
Hi. I like fix 1 and a bunch of errata actually in a fix. We've got a ton of errata for HPK 1. So those 2 things combined, I think, would make a nice bundle of work, and then the other 2 things could come as later.
Okay. Thanks.
Chris Wood, my understanding is that fix 1 is not actually fixing a problem. As Karthik suggested and demonstrated on the list, I guess, the proofs for HPK do not require anything beyond a CCA2 secure chem. They don't require any specific binding properties. And this isn't something that just holds for DH chem. It holds for any chem that is CCA2 secure. That's what the new proofs say.
What I would say is that we have guarantees of properties that we didn't know that we relied on via DH chem, that you try to swap out the chem in your Cypher Suite and HPKE for any other one, and you have to go revisit that.
That's what he did. He did that in the proof. He swapped it out for something more general, just a CCA2 secure chem, and the proofs follow through.
But proofs for in CCA, not for binding properties.
The only property that HPE purports to provide is CCA2 security for public key encryption.
Right. My argument is that we inadvertently have been relying on DH chem's properties, not in CCA, for binding to identities.
Which applications have been requiring or depending on properties more than CCA2 security?
The ones that have been using HPKE for encrypted client hello and MLS tree chem have, through their protocol, saved themselves from rebinding attacks and re-encapsulation attacks by doing things at the protocol level.
I don't think that's accurate for ECH.
What do you mean?
The analysis for ECH only depends on a CCA2 secure chem.
Right, but these re-encapsulation attacks would be present if they swapped out their chem in HPKE for classic Nicolese, and they weren't also committing to the public key as part of the transcript, they would be open to re-encapsulation attacks.
I'm not sure I agree with that, but I will yield my time.
Yeah, let's take that to the list. And it should be noted that there is errata for the HPKA, and at the very least, this presentation raises things that might be useful to include in errata. Next, after Chris, is Watson.
Watson, I think that if you have an application that's using auth chem, it might not know that it's going to need 2 separate keys instead of 1, and you have to worry about binding them together. So I don't think fixing up auth chem to use signatures is going to, in practice, be backwards compatible. I think if we have errata accumulated, it's a good reason for Abyss. I think the other stuff should be done as extensions and evaluated on the basis of, is this extension valuable?
Okay, thanks.
Right. Stephen Farrell, not necessarily against this. I'm also not convinced it's absolutely needed. If we do this, I think we should look at all of the various modes and see, is anybody using them? Because I believe there's a bunch of combinations that nobody uses, at which point we could maybe simplify things instead of just only making them more complicated.
So yeah, I think I agree with Chris that these, and I think with Watson, that these don't look like fixes. They look a lot more like extensions, right? HPK never purported to provide binding properties. You know, it inadvertently did with the HChem. So like maybe it would be nice to extend it as you've proposed to get those binding properties. I think it also looks like extensions in the sense that at least some of the things you've proposed here fit around the core HPE operation. Like the first thing you propose is how you define a Cypher Suite, right? Like you can define a Cypher Suite around your chem to have the nice binding properties when you flow it through HPKE.
Which
right?
is
You
kind
can
of
de-
what I did with MLChem for HPKE, which raised
Right.
these ideas. Yeah.
Yes, and you can do like a PSK combiner that feeds nicely in, right?
Mhm.
So it all fits around. So I think maybe this like bundle of stuff could make sense as like some recommendations for how to use HPKE and get some extra stuff out of it, but it doesn't feel like a fix or a V2 to me.
Mm.
I think Chris and Richard probably said everything I was going to do. I want less, like Stephen. I want less in HPKE than there is right now. There are too many bells and whistles already, and adding more. No, thanks.
So we're at time, and there's, yeah, the queue is closed. We can take this conversation to the hallway, and thanks everyone for attending.
Thank you.
Thank you.
So I didn't fully get what Chris was saying in terms of like part C. I mean, it says in the thing we're going to have two docs in the PQ.
I think there are at least two docs, but there is one document about requirements.
Yeah.
And a separate one instantiation.
Yeah.
Yeah. Can you? We are probably going to be distracted. Can you send us an email? Just as a reminder saying that in the I mean, we kind of need to balance because we have so many